Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson 2 on solving systems algebraically by substitution. Alright, so in this unit we're going to be concentrating on systems of equations, which we talked about in the last lesson. So make sure that you get caught up on that if you haven't already. We're going to see a variety of ways that we can solve a system of equations, and today we're maybe going to look at the most important one. In theory, you've actually seen solving a system by substitution back in 8th grade math, all right? But it's something that you probably didn't spend a lot of time on, and yet it's an incredibly important technique. So let's jump right into it and talk about solving systems by substitution. Now, there are many algebraic ways to solve systems of equations, as I mentioned. One of the most important, by far, is the use of substitution. So let's jump into it in exercise 1 and see how this works. All right, let's take a look. Consider the system given below and its solution x equals 4 and y equals 1, the system being 2x plus y equals 9 and y equals x minus 3. Letter A, show that 4, 1 is a solution to the system. All right, fantastic. Now I know it's a little bit weird because I'm giving you the solution right away, and then we're going to see how we can find it by substitution. But just roll with it for right now. What I'd like you to do is pause the video right now and show that 4, 1 is a solution to this system of equations. Go ahead and do that. All right, well, what we've seen in a previous lesson, or previous lessons actually, is that for this point to be a solution to this system, it's got to make both of these equations true. So let's do it. Simple enough. I'm going to write down my first equation, 2x plus y is equal to 9. I'm going to substitute the 4 in for x. I'm going to substitute the 1 in for y. Right? 2 times 4 is 8. 8 plus 1 is 9. And 9 equals 9. Right? That's true. All right. Now I'm going to take y equals x minus 3. This one's going to be even easier. I'm going to put 1 in for y, 4 in for x. I'm going to get 1 is equal to 1, and that's also true, right? So just as a reminder, right, for a point to be a solution to a system of equations, it's got to make every one of those equations true. So right now I know that one solution to this system is x equals 4 and y equals 1. All right, now let's take a look at letter B. Substitute x minus 3 in for y in the first equation and show that the value x equals 4 solves this new equation. All right, in other words, right, let's take a look at this system. In one equation, we've got 2x plus y is equal to 9, and the other equation is y equals x minus 3. Now, equality is extremely important, right? So because y is equal to x minus 3, I'm going to take that x minus 3 and I'm going to substitute it for the y up there in that equation. All right, so I've got 2x plus x minus 3 is equal to 9. Okay, now I want to show that x equals 4 solves this equation. There's two ways to do that. One way to do that is to take 4, substitute it into this equation, and show that it's true. The other way to do it is to solve this equation and see if the answer is equal to 4. Either one of them is completely acceptable, all right? In fact, I think I'm going to just solve this equation and show that x equals 4 solves it. In fact, right, I can do this by using the associative property of addition and simply, let me get my calculator out of the way, extend the page a little bit. Simply combine these like terms. I get 3x minus 3 is equal to 9. I'm going to add 3 to both sides. I'm going to get 3x is equal to 12. I'm going to divide both sides by 3, and I'll get x is equal to 4, right? So it's interesting, right? I knew that 4 was a solution to the system, but once I took one of the equations and I substituted it into the other equation, thereby eliminating the y variable, right? There's no y variable in this equation now. When I solved it, I found that x equals 4 solved that equation. Now let's take a look at letter C. Solve the system by finishing the substitution from B. All right, so I kind of did part of that already, right? I found that x was equal to 4. All right, the question is, how do I finish the substitution? Well, once I know one of the variable values, what I can then do is take that value and substitute it into either one of these two equations to solve for the other variable value. So at this point, I know x equals 4 is a solution to this system. I can put it into either one of these to find the y value, whichever one's easier for you. I would suggest that one, right? And I'll get y is equal to x minus 3, y is equal to 4 minus 3, and y is equal to 1. All right, or I, whatever. Y is equal to 1. All right. So the idea here is very, very simple with substitution, okay? And let's take a look at that on the next slide, right? The principle of substitution. One of the single most important properties of real numbers is that of substitution. Equals may always substitute for equals, okay? Forget about solving a system by substitution, right? Any two things that are equal can replace each other, all right? And we see this all the time, right? Sometimes I'll replace something like 1 plus 3 with 4, because 1 plus 3 is equal to 4. Or I'll replace 12 halves with the number 6, because 12 halves and 6 are the same thing. It just makes sense. If two things are equal, they're the same, and therefore they can interchange for one another. And we can use this amazingly important idea to solve systems by substitution, right? So let's take a look at how that's done. It's really cool, and it's one of the most important ideas in math. Let's take a look at exercise 2. Solve the following systems of equations by substitution. Letter A, y equals 2x plus 5, and y equals negative 3x minus 10. All right, so I've got these two equations. Now notice, both of them are solved for the variable y, okay? So y is equal to 2x plus 5, and y is equal to negative 3x minus 10. What I can do is for one of these two y's, I can substitute this in. So what I'm going to do is I'm going to take this 2x plus 5 and I'm going to replace that y in the second equation with what y is equal to from the first equation. Now what's really cool here is there's two things that have gone on that are very important. One, I've taken two equations and combined them into a single equation. The other thing that is very important is that I now have an equation with only one variable. And of course I can solve that. Let's do that together. I can solve this by maybe first adding 3x to both sides. Right? When I do that on the left side, I get 5x plus 5. On the right side, those two cancel and I'm just left with negative 10. Be careful there. Now I'll subtract 5 from both sides. And I'll be left with 5x. Again, be careful here. Negative 10 minus 5 is negative 15. And finally, if I give myself a little bit more room, I can divide both sides by 5, and I can get x equals negative 3. Now, note at this point, right, what I've come up with is the x value that is part of the solution to the system of these equations. I now need the y value that goes with it. How do I find that? I take this x value and I either substitute it back into this equation or this equation, because remember, x is negative 3. So I can substitute negative 3 wherever I see an x in either one of these equations, and I can find the y. By the way, it shouldn't matter which equation you substitute it in. You should get the same y in both cases. So I'm going to substitute it into the first one. Right? The first equation is y equals 2x plus 5, I think. Let me just check. Yep. So y equals 2 times negative 3 plus 5. That's y equals negative 6 plus 5. And that's y equals negative 1. So the solution to my system is negative 3 for x and negative 1 for y. Or if you want to write it as a coordinate pair because you just need to do so, you could say that the solution is the point negative 3 comma negative 1, right? So that's it. Now, substitution, like all things in math, has its easy applications, like the one that we just looked at, and slightly harder ones, like in letter B. So I'd also like to take a look at letter B together. Let's take a look at the system. 4x minus 2y equals 16, and y equals negative 5x plus 13. Now notice, in letter A, both of these two equations were solved for y. So I could take what y was equal to in one equation and replace the y in the other one, or vice versa. I could have taken that negative 3x minus 10 and replaced this y with it up here. Wouldn't have made any difference. My solution would have been exactly the same. Here, notice I've got an equation that is not solved for either variable and one that is, okay? And what that tells me is I should now take my negative 5x plus 13 and substitute it in for this y. Now I have to be very, very, very careful when I do that, because this y in this equation is being multiplied by 2 and being subtracted. I need to make sure that I multiply this entire thing by that negative 2. So let's do that substitution right now. All right, give myself a little room, bring that all the way up to the top. Here we go. So I'm going to have 4x minus 2, and get some parentheses in there, times negative 5x plus 13 equals 16. I have just substituted what y is equal to in the second equation into the first one. Now I need to multiply through this parentheses using the distributive property by negative 2. Negative 2 times negative 5x is positive 10x. I have negative 2 times positive 13 is negative 26, and that's equal to 16. I can now combine these like terms. I have 14x minus 26 is equal to 16. Add 26 to both sides. All right, I will get 14x is equal to 42. Sorry, almost added wrong there. Divide both sides by 14, and 42 divided by 14 gives me an x equals 3. Again, simple enough. Because this equation is solved for y, that's how we put it, it's solved for y, y is all by itself, I'm going to take that negative 5x plus 13 and I'm going to substitute it into this equation. The biggest key here is to get it in parentheses so that it reminds us that we have to multiply that entire expression by negative 2. Now, once we have that x equals 3, I can substitute it either into the first equation or the second equation and figure out the y variable. Now, in this particular problem, I could have easily taken that negative 3 and plugged it into either one of these equations to figure out y, because they were both solved for y. In this situation, it's going to be easier to put the positive 3, into the second equation, simply because if I put it in the first equation, it's just going to take me more work. Anyway, let's do that. Let's now take that 3 and plug it up here. Y is going to be, negative 5 times 3 plus 13. Negative 5 times 3 is negative 15 plus 13. Negative 15 plus 13 is negative 2. So I could just leave my answer like that, or if I wanted to express it as a coordinate pair, I could write it as 3, negative 2. All right. The principle of substitution is so amazingly important when it comes to solving a system of equations. Almost every system can be solved by substitution. Even later on in this unit, when we find other methods of solving systems, you could, at the end of the day, solve every one of them by substitution, and it is the most important technique of all. It's also very easy to understand, right? Substitute one equation into another. Now, the technique of substitution works particularly well when we want to algebraically find the intersection point of two lines, right? Remember the last lesson. In the last lesson, we actually graphed two lines, found their intersection point, and said, well, that's the solution to the system. But what if we want to actually find the intersection point without graphing the two lines? Let's take a look at that in exercise number 3. Consider the two lines whose equations are shown. Y equals 3x minus 31, and y equals negative 2x plus 89. Letter A, find the intersection point of these two lines algebraically. Now, side note, you can imagine, right, without using your graphing calculator, which we are in a minute in letter B, you can imagine how ugly that would be to try to do by hand. I mean, this first line, it's got a y-intercept of negative 31, and that second line's got a y-intercept of 89. I can't even imagine trying to solve that by like taking out a blue piece of graph paper, drawing axes on, that'd be nuts, right? But solving it by substitution is pretty easy. So I'd like you to pause the video now and try to solve letter A. Just look back at the last exercise, letter A, and it's nearly identical, and find their intersection points by solving that system. All right, just like exercise 2, letter A, because both of these equations are solved for y, I can substitute either one of them in to the other one. Actually, I think I'm going to do it the other way around. I'm going to keep that 3x minus 31 on the left. I'm going to substitute that down here. It really doesn't make any difference, but I'll have 3x minus 31 is equal to negative 2x plus 89. All right, so I'm going to add a 2x to both sides. All right, so far so good. We've got 5x minus 31 is equal to 89. I'm going to add 31 to both sides. 5x is equal to 120. I'm then going to take 5x and divide it by 5, and 120 and divide it by 5. What is that? 120 divided by 5 is going to be 24. Is that right? Might as well just check. Never hurts. Let's see, 120 divided by 5. Yep, 24. Great. Now I want to figure out what the y-coordinate is. Just like before, I can take that and substitute it into either equation. I think I'll just plug it into the first one. Y equals 3 times 24 minus 31. And I'll let the calculator figure this one out for me. We're going to have 3 times 24 minus 31, and that gives me a y of 41. So my intersection point is at 24, 41. All right, again, that would be extremely difficult to do if I was doing it by hand in any reasonable graphing situation. All right, let's now verify our answer using our graphing calculator. It's one of the wonderful things graphing calculators can do for us is it can find the intersection point of two lines. So let's take a look at that in letter B. Letter B. Use your calculator to graph both lines and use the intersect option on the calculator to verify your answer to A. Think about how to use your answer and facts about the lines to set a good viewing window. All right, let's talk about all this, right? First, I'm going to write down that intersection point right here so that we have it and we can think about it, right? Let me bring up my TI Inspire calculator by Texas Instruments. I'm going to go over and put in a graph. Here we go. So F1 is going to be my first line, 3x minus 31. Unfortunately now I'm going to go into menu and 3 and function. I'm going to put in F2 is negative 2x plus 89. All right, I don't even see that line. Now, side note, I don't think this graph is doing me much good here. And that's probably because if you think about it, right, this graph goes from negative 10 to 10 on the x-axis and from roughly negative 7 to 7 on the y-axis. It's not even that nice, okay? I want to set this window so that I see this intersection point. So I got to make it big enough so I see 24 and 41. But I'd also like to kind of see the lines. Now keep in mind, this one has a y-intercept at negative 31, and this has got a y-intercept of 89. So let's play around with this. Let's go into our menu. Let's go to option 4, which is window, and let's go into our window settings. Now, I don't need a lot of negative x values given where my intersection point is, but I think I'll keep x equals negative 10. That's fine. All right, now they intersect at an x value of 24, but maybe I want it a bit bigger than that. Maybe I'll go with an x value of 50. I'll let the x scale be automatic. Now my y scale, that's a little bit more interesting, right? I've got this y-intercept here at negative 31. So I want to make my minimum y less than that. Maybe I'll go negative 50. That should be good. Now my y-intercept of this line is positive 89. So maybe I'll make my y maximum 100. All right, that should be good. And look at that. You know, now I've got this beautiful graph, right, that's got both my lines on it, okay? And now let's take a look at that intersect command. Okay, so at least on the TI Inspire, to get the intersect command, I'm going to hit my menu button. That's my main button on this calculator. I'm going to go down to Analyze Graph. That's option 6. Intersection is option 4. it says it wants a lower bound. So what I'm going to do is I'm going to move that vertical dotted line with the finger there to the left of my intersection point and hit enter. As soon as I do that, I'm then going to just use my touchpad to stretch it across to the right of the intersection point. I'm going to hit enter. And then at least on this calculator, what's beautiful is it just shows me the intersection point, 2441. I would circle it on the graph, but that doesn't work that way. All I can do is kind of do that, and that just didn't work. Although that was kind of cool. It did make a little mark there. One of the great things about the graphing calculators is that you can very quickly use them to verify something like this, right? Important to be able to find intersection points using your calculator. We'll spend an entire lesson on them eventually. Huh, and that blue line just came right with it. All right, let's keep going. Now, systems often arise in word problems, and we'll spend a couple lessons just working on word problems with systems, but we can do a little bit of it now, and they often will arise in word problems when there are two obvious variables and two pieces of information that relate those two variables together, right? It makes sense, right? A system is two or more variables along with two or more equations. In this class, a system will always be two variables, two equations. That's it. Let's take a look at exercise number 4. Max and his father Kirk are comparing their ages. I wonder who they are. They know that the sum of their ages is 52 and that Kirk is 7 years older than 4 times Max's age. If Max's age is represented by M, that makes sense, and Kirk's age is represented by K, also makes sense, write a system of equations that models the information given in the problem. All right, so I'd actually like you to pause the video right now and see if you can use the variables M and K along with the two pieces of information they gave to write down two equations that constitute the system that describes what's given in this problem. Pause the video now and see if you can do that. Well, okay, what are the two pieces of information? One, we know that the sum of their ages is 52. That's easy, right? M plus K is 52, right? M is Max's age, K is Kirk's age, their sum is 52, M plus K is 52. It doesn't get any easier than that. Now, the other piece of information is that Kirk is 7 years older than 4 times Max's age. So Kirk is 4 times Max's age plus another 7 years, right? Remember, I always want to be thinking about that multiplication first and that addition second because of order of operations. Two equations, two unknowns, it's a system. Let's take a look at letter B. Solve the system using substitution to find both of their ages. Awesome. Well, it doesn't matter whether they're X's, Y's, or M's and K's. You do it the same way. Pause the video now and see if you can solve this system by substitution. All right, well, it's relatively easy, primarily because we've got this second equation that is solved for the variable K. So what I can do immediately is I can take the 4m plus 7 and substitute it into this equation for that K, giving me m plus 4m plus 7 is equal to 52. I can now combine the m and the 4m to be 5m plus 7 is equal to 52. And now I'm off to the races. I'm going to subtract 7 from both sides. I'm going to get 5m is equal to 45. I can divide both sides by 5. And I find that m is equal to 9, right? So Max is 9 years old. Let's figure out Kirk's age. Kirk is going to be 4 times Max's age plus another 7 years. Extend my page a little bit. Kirk is going to be 36 plus 7. Kirk is going to be 43 years old, or at least he wishes he is. All right, so Max is 9, Kirk is 43, and we've just solved an easy system by substitution. All right, you probably even played around with some problems like this back when we only had a single variable. And back then, we probably let m be equal to Max's age and let 4m plus 7 equal Kirk's age. But now we can be a little bit more sophisticated. We can have the two variables, we can write down the two pieces of information we've been given in terms of those variables, and then we can use substitution to figure out the values of the two variables. All right, let's do one more problem. It's a little bit more messy, and you're definitely going to want your calculator on. All right, here we go. Exercise number 5. Two cell phone plans offer differing text packages. The two plans are outlined below. Plan A, $9.25 per month charge, along with a charge of $0.06 per text, or 6 cents per text. Plan B, $2.50 per month, along with a charge of $0.15, or obviously 15 cents per text. Is there a certain number of texts when the two plans cost the same amount? Determine your answer by modeling the information given in the problem with two equations and then solving the system you created. All right, cool, right? So let's come up with equations, and they're going to be pretty easy, that model how much each plan costs based on the number of texts that are sent, right? So for plan A, it's pretty simple, right? The amount that we are charged is going to be what? Well, for every text sent, right, maybe I'll call it n for the number of texts, we're going to be charged 6 cents, so 0.06 times n. But then we've got that like set monthly charge of $9.25. For plan B, very similarly, right, the total money that we're charged is going to be 0.15 times the number of texts sent plus $2.50. Okay, so those are simply the equations that are predicting how much we're going to pay for each plan based on the number of texts that were sent, right? Now, by the way, it would be completely okay to rewrite these models as 925 plus 0.06 times n and 250 plus 0.15 times n. It may even be a more sort of natural way to think about it. Oh, well, I'm starting with 925, and then for every text, I'm having to pay another $0.06, similar with the 250 and the 0.15. Now we need to solve this system by setting the two equations equal, i.e. substituting one equation into the other. Pause the video and see if you can work through the somewhat messy decimals in this problem to figure out the answer. Now, really, the answer is yes or no. Is there a certain number of texts when the two plans are the same amount? All right? Pause the video now and try to solve this system. All right, well, again, since both of these equations are already in terms of y equals, I can either substitute this one into this one or vice versa. I think what I'm going to do is I'm going to take this particular equation and I'm going to substitute it into this one, and we'll start that maybe right here. So I'm going to get 0.15n plus 250 is equal to 0.06n plus 925. By the way, I let something slip there for a moment that I want to mention. I said you set the two equations equal. Math teachers will say that all the time when you're using substitution to solve a system where both equations are solved for the same variable. Notice both of these are y equals, right? And when I use substitution, it appears that I'm taking this equation and I'm setting it equal to this equation. So you'll oftentimes hear teachers say, well, set the equations equal. And what they're really saying is substitute one equation into the other. All right, with that out of the way, let's finish solving this. I think the first thing I'm going to do is I'm going to subtract a 0.06n from both sides of the equation. Now, if the decimals are confusing for you, don't hesitate to pull out that calculator. 0.15 minus 0.06 is 0.09. So I get 0.09n plus 250 is equal to 925. I'm now going to subtract a 250 from both sides. And again, if the decimals are bothersome to you, I think I'll take this up here next. 0.09n. They're going to become bothersome to me in just a second. Hey, why not right now? Now I'm going to go, ooh, my calculator got tiny. There, it's getting a little bigger. Okay, I'm going to go over to my actual screen here. Wow, that is just horrible. There we go, that's a little bit better. 925 minus 250 gives me 675. So I got 675, and now I'm going to divide both sides by 0.9. 0.09, and n, got to keep moving my calculator around, maybe make it a little bit bigger. There we go. 675 divided by 0.09 gives me 75. So you bet, right? The answer is yes, 75 texts, right? Now you might say, well, why didn't you take the 75 and plug it back in to finish solving the system? Well, keep in mind what the question asked, right? Is there a certain number of texts when the two plans will be the same amount, right? Well, the answer is yes, 75 texts. The question does not ask what is the amount that they will be when we hit that certain number of texts. So there's no absolute need to take the 75, plug it back into one of these equations and find out how much we were actually charged, right? All we need to do is really just say, yeah, 75 texts. All right, let's finish this thing up. So we've now had a couple lessons on systems of equations, right? Two or more equations with two or more variables that we are trying to solve to find the values that make all the equations true. One of the absolute primary ways that we do this is by substituting one equation into the other. And that's very convenient to do when one equation has one of the variables isolated, all by itself, y equals, x equals, n equals, whatever. And you can simply take that, substitute it into the other equation, and eliminate one of the variables. Once you've eliminated one of the variables, you can solve the resulting equation for the variable that remains, get that value, substitute it back into either of the original equations to find the value of the other variable. This is something that you will do in math as long as you stay in math. You could be taking math as a junior in college and you will still be occasionally solving a system by substitution because it is such a widely used tool in math. All right, so more on this obviously as the course progresses. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.